feel a little bit better, but at this moment I can do nothing. Sorry about that. Maybe I can.
Hey, can you
Hello.
try to write something on the paper so we can try to see if it's clear?
That okay?
Well, actually, that looks pretty good.
Yeah, but what I worry about is this area. So if I wrote something on this area, then maybe it's a little bit dark. But I'll try. Yeah. If you do have anything that you cannot see clearly, let me know immediately. Okay, so that I can change and maybe hide something or okay. So before we move on, well, today we are going to discuss a little bit more about those kind of important PDEs, how we can get them, and how to formalize the problems, okay? And the last time we mentioned a little bit about the transport equation, but it seems that, well, you are not quite clear about the transport equation, so maybe today I'll first try to use two other ways to expand the transport equation. So other than that, any question about this course, about anything? By the way, last time somebody say that, well, it seems over too hard, this course. Well, to be honest, this is the first week. So what we are discussing about is the background of this course, okay? So it might be slightly hard because it involves a lot of physics. Although it's very important to know some physics when you try to learn PDE, because after all, this is applied math, so you will have to use it to real problems. But in the sense of this course, those kind of physical background, if you are not able to understand it, that's totally fine. Because whatever it is, whatever physical background it is, it just helps you to understand the problem, okay? It's not the problem itself. You can forget every physical background and study math, well, directly. It doesn't matter, but to know a little bit about physics will help you based on my experience, okay? Which is why in this week, I try to introduce some kind of physics or some kind of geometry of a PDE. And this kind of thing is not as precise as math, but it's something like an intuition. Okay, it can help you to build your intuition about the PDE. So if you do not understand it, it's fine. If you do not understand, well, how the picture looks like, it's totally fine. You just need to know, well, what kind of math we are doing, okay? And the content in this week will be different from, somehow different from, well, what we are going to discuss, well, in the rest 6 weeks of this semester. It will be somehow different, which also means that it will not wait a lot when you try to do the final, okay? It will not wait a lot, but this is helpful, okay? I'll say this is really helpful if you try to use the PDE as a tool, as a mathematical modeling tool, okay? So any question? Any question?
With an organizational kind of issue, honestly, I kind of feel like looking at the screen that's like super, super bright is kind of painful for my eyes for like 5 minutes so far. Do you mind, like, I don't know, but today is like your light is like very, very bright, so it kind of hurts eyes. Can you try to make it like dimmer? I don't know. Sorry, that's a concern.
Okay, maybe I can try to just for my face, right? Or is for also for this picture, also for this
Yeah, for the paper mainly,
for the paper
because
as well.
super, super.
How about this? Does it looks better, or does it looks better in this way?
Yeah, this looks much, much better. Thanks a lot.
Okay, yeah. Then yeah, let's try to write it in. Okay. Any other question? Any question?
Will you suggest, will you recommend us to take some physics course in the future? I may have a lot of space to take alternative courses apart from math.
That's a good question. Well, it depends. You know, in math, it has different areas, right? So if you are interested in algebra or geometry, then I don't think it's necessary. to take a lot of physics. Of course, it's helpful, but it's not really directly relevant to what you are interested in. But if you are interested in analysis, especially in PDE or ODE, then it's better to take some physics class, something like fluid mechanics, or those kind of quantum mechanics. Those kind of thing will be helpful. But I mean, if you are really interested in this area, then of course it's still not necessary to take those kind of physics course in your undergrad study. Okay, you can take that in your grad school. That's also fine. Okay, so it depends. It depends. Well, right now, what I'm saying is, since a lot of you may not want to get a PhD in math, so in that situation, then of course, the reason why you are interested in PDE is, well, first, you want to learn how to do a modeling, right? You want to learn how to do a modeling and how you can understand a math model. Understand in the sense of, common sense or some physical sense. And then second thing is, well, maybe the method of PDE, of how to deal with a PDE, is not that useful, because some of the methods we learn in this semester are quite theoretical and they are really pure math. Okay, but I think it will be helpful. It will somehow be helpful if you learn something about a Fourier analysis, which is something I'm going to discuss starting next week. Okay, this Fourier analysis is something really useful. Whatever you learn in the future, it will be really helpful, and it's quite amazing. Okay, and it's also very useful in PDE, of course. So, which is why at the first week I try to introduce something like intuition about PDE, and second and third week we are going to discuss some Fourier analysis, and then after that we will do some theoretical PDE. Okay, is that clear?
Yes, thank you. Super clear.
Mm-hmm. And any other question? Okay, maybe I should write it this way. Will it better? Because then I can see that, well, if I wrote somewhere here, then it's very hard for you to see. If I write it this way, will it better or not? Let me try to write it this way. Okay, otherwise I think it will hurt your eyes. So, as we mentioned last time, well, we try to study the transport equation. ut plus b dot ux equals to 0. Okay? This transport equation. And then we mentioned that this transport equation, if you assume this u, it's actually the concentration. Concentration of something, for instance, a lot of particles, or you can think it's some dials on the water, or it's a piece of oil inside, well, on the water. Then this somehow means those kind of concentration can be transported at speed b. Okay, and we mentioned that, for instance, in 1D, this is somehow like you have a few particles on a line. Then you give each particle a speed. For instance, b is a constant, and then that means you make those particles move towards, this is x, this is x-axis. You make these particles move towards this x-axis at speed b. Okay, and for some of you, it seems a little bit hard to understand why this is this is true. Although you can check that it is true, but it seems very hard to understand why it is true. So maybe I'll give you another example, and to get this equation, which is an example, which is another explanation in your textbook. Okay, this kind of method is so-called the control volume. Which is super useful when you try to learn the mechanics. Okay, this is well, you can imagine a problem like this. suppose you have a pipe, okay, a water pipe or whatever pipe here. And on the pipe, there is, well, a piece of pollutant, okay, or a piece of oil, like a piece of gas oil or whatever, okay, something bad here, okay, something like oil or some pollutant or whatever, okay. But this piece of things, it may have, well, it may contains a lot of materials, it may contains a lot of chemical stuff. And so, well, at each point, you may have a, well, somehow a different density, okay? Then U is a concentration. That means, okay, U at X gives you at this point, say X, at this point X, the density of this kind of thing, okay? You can try to imagine this water pipe is just a one-dimensional stuff. And this Ux is basically, okay, the density at point X, okay? Then what happens is, well, since time flies, you can imagine this piece of stuff, it can move towards this, well, right direction, okay? So that's constant speed, C. Okay, C is a constant. Then what we want to know is, well, is UXT. Now this one is UX0, but then we want to know what is UXT, which means after a while, maybe this stuff moves towards to this direction and it in this position. Then what you want to know is at time t, what is the distribution? What is the distribution of this pollutant? Okay. This is the meaning why we are interested in this concentration function. Okay. At different time, what is the distribution of density of this part, of this stuff? So if we would like to learn that, then how can we build an equation to help us to know that? This would be a problem, right? Now you can see that this is not only for one point. If it is one point, you can, of course, build an equation that is an ODE, right? If you only have one point on a line, say this point is X, we know that this point moves towards the right direction at speed C. Then that means, okay, the displacement satisfy an ODE, right? The displacement of this, let's say this is O, well, of this point O, the displacement of this O is X, then we know that, okay, X dot equals to C. Then you can solve X, right? You can solve, okay, at time T, where is this point? But now the problem is, well, you try to describe, well, not only one point, but a lot of stuff. How does this stuff change? Okay, how does this distribution change if you have a constant speed? Then in this situation, you will have to use the PDE tool, okay? Which means, well, we can somehow use this so-called the control volume. That is, you try to make a black box or what kind of box, well, some kind of box here on your water pipe and look at this, this box, okay? Then what we do know is inside of this box, there are something, right? There are some, well, for instance, there are some this chemical stuff or whatever stuff here. Then what you do know is the total mass of this chemical stuff can be computed, right? How to compute it? How to compute it? Well, suppose this point is 0 and suppose this point is B from 0 to B, okay? Then inside of this area, what is well, total mass of your chemical stuff? As long as you know the density, you know that, okay, it must be able to write as from 0 to B, you take this integral, and this U xt, at this moment, this is a distribution at time t. This is a distribution of your chemical stuff, dx, right? You take the sum up of all this kind of density, okay? How many, well, what is the density here? What is density here? Well, this is a two-dimensional problem, but let's assume it's actually a one-dimensional problem, okay? What is the density at this point? What is the density at this point? And the density at this point, and so on. And you can take a summary of them, summary of the density, then what you get is the total mass of your chemical stuff, okay? Then this is what happens at time 0, for instance, at time, well, at the initial time. Then after a while, well, let's say at time, this time, let's say it's t0, then at time, after time h, so which means at time h plus t0, what happens is this stuff, as you see, at speed c, it will move towards the right-hand side at speed c. So that means, well, first, the total mass will not change, okay? But this this mass, this piece of mass will move, will have a, well, transition, right? It will transport, it will move. It will move to somewhere, well, with distance ch, right? So which means now the total mass should equals to from ch to b plus ch, okay? Of u, well, x, let's say this is t0, then this is t0 plus h dx, okay? This is a conservation of mass, okay? So you know that these two are the same. This is the only thing you know, right? Okay, now you can see these two guys are the same, right? Then what happens if we try to shrink this, this kind of volume U control? Which means let's try to take the derivative of B. Let's take partial B both sides and see what happens. Okay, this M, of course, it depends on B, right? This M, it depends on B. Well, how much mass you have depends on what kind of a window you are looking at. Okay, let's take partial B both sides and see what happens. If you take partial B on this side, well, this is what? This is actually, okay, so
Fundamental
theorem of calculus. Great. This is fundamental theorem of calculus, so you can simply plug in B, right? Plug in B by X. So on the right-hand side, what will on this side, you get UB T0. Okay? On the left-hand side, only this upper limit depends on B, right? So it's equals to UB plus CH T0 plus H. Okay, that clear? Now, let's try to do one more step, which is, since you take a little bit ahead of time, right? You take time t0 plus h. So let's try to make this h shrink and see what happens, which is, let's take partial h both sides. Then, on the right-hand side, you got 0. It doesn't depend on h. On the left-hand side, if you take the derivative, what you get is, well, the derivative of your first component or the first variable, which is partial x, times the derivative of inner part in terms of h, which is c, plus the derivative of the second part, which is.
Would you mind shifting your paper a bit? Because we don't.
Sorry. Yeah. Okay. So you get this. And so, or partial tu plus c times partial xu equals to 0. You can take h equals to 0. Okay, you take the derivative in h and then take h equals to 0. Then what you get is this guy. Okay, so this is how another way to get, well, this transport equation by look at the whole picture, a bigger picture, and using this kind of control volume method. Any question before we move on? Any question? Okay, I put it here. Well, this sounds like something, well, I hope that something makes sense for you. But this is actually the whole picture, right? It's a bigger picture. However, if you try to take a deeper understanding of what happens, basically, it's like what? It's like, well, this is one-dimensional. Or again, this is one-dimensional. But if you try to understand it in the sense of two-dimensional, okay? Try to understand the transport equation in the sense of two-dimensional. What's the meaning of that? What's the meaning of this transport equation in two-dimensional? So that simply says that you may have something, well, some chemical stuff on some area or whatever, okay? Then at each point, this U represents the distribution of density, right? So which means at each point, this U at this point gives you the density at this given point, okay? Or if you try to see everything just like some particles, then this U represents how big or how weight, what is the weight of your particles at point X, okay? And then, as we mentioned, this B simply means all the particles move, well, towards at speed B, okay? So in two dimension, B, suppose if you try to release the restriction on B a little bit, this B can depend on X, right? So then in this situation, the transport equation, which write as B dot gradient U equals to 0, we can write it this way, simply says that at each point, you have a particle. This particle, this U tells you this particle, how big this particle is, okay? The density of this particle. And this B just tells you this particle at each position, for instance, at X position, will have a speed Bx, okay? So for different P's, for different particles, it may have different speed. And then, well, different particle have different density described by U, and this different particle, well, at different position will have different speed, which is B, okay? Then this transport equation simply tells you the story that suppose you gave me a velocity field on dimension 2, okay? And you have some kind of chemical stuff on dimension 2. And then you let this chemical stuff to move along your direction field. Then this U xt simply means at time t, the distribution of your particles, okay? In dimension 2, maybe it's a little bit hard for you to imagine, but in dimension 1, it's a little bit easier, okay? It just says that at different points, you may have a different density of your material, okay? And at different point, you may have different speed, which is given by Bx, okay? The speed depends on X. And then, well, this particle will try to move. For instance, at the very beginning, it's this one, this is this particle, and this particle may try to move towards here, and then it moves here, then maybe the velocity also change. And then it moves to the next one, then the velocity again change. And then what you want to find is the distribution after a while. The distribution of the particles after a while. Okay? So this actually gives us an idea about how we can solve this transport equation. If you try to look at it as the movement of particles. Okay? This gives us an idea about how we can, find a solution. That is, we want to find the distribution of your particles or distribution of your materials or this kind of liquid or whatever, okay? The pollutant. Then that means what you want to find is, well, after a while, what is the position of the particles, okay? After a while, what is the position of your particles? So which means we basically want to find the trajectory. I don't know whether you know this term or not, trajectory of a point, say x0, okay? Which means your x0, say in dimension 2, okay? Your x0 is here. Then you start to fluid. You start to put a direction field on this plane. Then this x0 may try to move, well, whatever, and then at time t, it moves to xt. Okay? So as long as you know this movement of each particles, you basically know the distribution of your solution U. Or the distribution of your concentration. As long as you know everybody, right? As long as you know all these particles at each moment, the speed of it, so that you know the displacement of each particles on this x-axis, as long as you know the displacement of the particles at each moment, then you basically got, you should be able to get the solution U, which is, after a while, what is the distribution of your x? Okay, what is the distribution of your density? So that means we want to find a solution to an ODE, right? We want to find, for instance, the solution to this following ODE, because you know at each point what is the speed at this point, right? The speed is always bx. So which means you want to find a solution to this ODE. This xt is a trajectory. Let's say xt is a trajectory. Okay, this maybe not a good, well, this may not be a good notation, so let's try to change the notation. Say xt starting at x0, okay, this is a trajectory of x0 at time t over dt is actually equals to, well, this derivative must equals to b you evaluate it at this point. As long as you know that at time t, this x0 t is at this position, then you plug in, you got the velocity at this point, of course, at this time. Okay, this b may also depend on time. So then what you get is an ODE, and x0, 0 is equals to x. This is a very standard initial value problem. Okay, so this will tell you all these particles, how they can move. Okay, but this doesn't help us, right? It doesn't really help us because it will not solve the PDE. Remember, we're trying to solve this PDE. But now it tells me, okay, of course, physically, if we know everybody will, after a while, where they are, then we should know the distribution, right? We should know the concentration, UXT. But mathematically, this is not so easy to see. Okay? Then how we can solve that? How we can from this intuition to solve this PDE? Well, let's see, okay? Now suppose you have a solution for arbitrary x0 and arbitrary t. suppose you have a solution. Any x0. We have a solution x0 t. Okay, this is a trajectory. Then what we have is we know that the density at this point, we know that this particle is just a move, right? It moves starting from x0 and then eventually it moves to this point at time t. Then we know that the particle is still particle, right? So which means this particle, although it moves, it will not change the density, right? So it's actually equals to u x0 at 0, right? It equals to, at time 0, the density at x0.
Oh, sorry, a quick question.
Of course.
So if we would want to go and like reread that part, like about that, which textbook should we use? Like, is it Walter?
This one? This part. I mean, this part, this understanding part. I think you cannot really find the textbook to find this part, but the result you can find it on stress. Okay, you can find on the water stress book, and this part is also on water stress book. But this part, how you can guess the real solution part, well, this is something from several lecture notes and textbooks, and it may not be easy to see directly. But you can also find some kind of explanation from other direction from Strasbourg, okay? But basically, this is the idea. This is just the idea. And the final result is just a math result. But what I want you to know is you know how you understand this result, okay? Well, then, as long as you know this guy, you are able to solve it. The reason is, well, you want to solve eventually what is uxt, right? But then you find that what you want to solve is, what you know is, you know that eventually if you have, okay, if you know this point, if you know it is the solution starting from this point, then you know what is value, right? But then this is not good enough. So if you want to solve it backward, instead of write this something in the sense of the initial data, something like initial data. We'll introduce initial data a little bit later, but let's use this term at this moment. If you try to start from this side and write it in the sense of your initial data, then it's still not so hard. What you need to do is you just need to go backward, right? If you go this direction, you go from t equals to 0 to t equals to t of this solution to this ODE system. But if you go the time reverse, okay, if you go back to the past, then what happens is it should be at time 0, starting from this point x, okay, do a time reverse. Then this is your solution, okay? You're starting from this point and you go back in time and see what is your x0. You starting from, you already know this point, you already know this point. You go back in time at t times, and then what you will get is, what is your initial data? Okay? This is somehow abstract. I agree, it's somehow abstract. And you may not understand it at the very beginning. But let me show you a few examples so that you know, okay, it's not that hard. For instance, okay, let's say we have this ux plus c, well, I'm sorry, ut plus cux equals to 0. We have this equation. Then how can we solve it? As we mentioned here, we want to solve an ODE. Okay, we want to solve an ODE for the particle trajectory. Okay, which is we want to solve dxt at x0 dt equals to bx, which is c, a constant. Okay, so with initial data x0 equals to x0. That's easy. That is, well, x0t equals to ct plus x0, right? Although I don't assume you know how to solve an ODE, but I believe everybody knows how to solve this ODE, right? This is this initial value problem is really easy. I think when you learn this fundamental theorem of calculus, you know how to solve it. Okay, we have this solution, okay, the general solution. Now let's see. Our general solution to our PDE should be written in this way. Okay, so that means the general solution to our PDE should be equals to u x minus t starting at x comma 0. Okay, so it's equals to ux minus ct 0, which means as long as you tell me what is your initial data of your PDE, as long as you tell me what is ux0, then the solution is fx minus ct. Okay, that clear? Well, maybe it's not so clear, but let's see another example so that I think it's enough for you. You're smart enough to understand how we can solve it, no matter whether you understand this process or not. Okay, now let's change it a little bit. Let's say you have an x here. Okay, then as we mentioned last time, this means you have the level set of u. The level set of u should be something like this curve, which is c e to the t, right? Those kind of curve. Y equals to c, well, x equals to c e to the t. Those kind of curve are the level set of u. But now we actually are able to solve them. Okay, that is, again, you want to solve this weird notation, although it's very weird, but it's just notation. Okay, you want to solve this kind of ODE, right? This is equals to bx. Now your bx is x, so it's equals to xt x0. Okay, and x0, 0 is x0. Again, this is not so hard to solve. Fortunately, this might be the first ODE that you have seen in your ODE class, right? That is, x0t should equals to x0 e to the t, right? So that means uxt should equals to uxx minus t as 0. So it is x e to the minus t 0. So if ux0 equals to fx, then your uxt should equals to fx e to the minus t. Okay, you can, if you are worried about it, you can try to plug in and see, yes, this kind of function is indeed a solution to this differential equation. Well, we can try if you want. Okay, if you try to plug in here, then the derivative in t of this fx e.
Sorry, can you use the paper a bit?
Yeah. sorry. And then this first term will gives you, okay, x e to the, well, minus t. You take derivative of it in terms of t. And f x e to the minus t prime. Okay, so this is minus x e to the minus t and f prime x e to the minus t. Okay, let me lift it a little bit. And partial x f x e to the minus t will gives you, oh, that's even easier, f prime x e to the minus t, and you take this is partial t and partial x e to the minus t, which equals to e to the minus t f prime x e to the minus t. Okay, so this guy plus x times this guy equals to 0. Okay. Any question? Okay, any question? So this is a basic idea about the transport equation. Next week, we will see more. We will see a little bit more example about the transport equation, which is more interesting. Okay, but you can see that, okay, at least in general, the solution to a transport equation should be very easy. However, it is easy, but not so easy, because transport equation is also part of my research, okay? I'm doing research on transport equation, and there are a lot of very interesting things you can do on transport equation. Any question? Any question?
Sorry, I keep on forgetting what we had in the beginning. How did we get that the x(0 t) by dt is x(0 t)? Yeah, how did we get that equation?
We got this equation simply we try to interpret it in the sense of particle movement. Okay, so we say that this transport equation, it just says that every particle will you have a direction field on your plane. Okay, and that makes every particle just move at different point, then you move in a different speed. Okay, and then what you want to find is the trajectory of each particles, so that together you get the distribution of particles, which is the concentration function, right? So which is why you want to solve, because at each point you will have a velocity, right? So that means if you want to find the trajectory, if you want to track each particles, then you have to solve this ODE. This ODE means at this point you have this the speed b, right? At this point you have speed b as well, and so on.
Okay, I see how you get it from like a picture, but how do you relate the picture to the initial transport PDE? Because
that's a good question. If you have the solution to this guy, right? If you have the solution to this guy, and then that means, okay, you have the solution can be writing in this way. This u. This guy is the physical explanation of the concentration, right? It's just the particle movement. The particle will try to move, but the concentration will just change in this way, right? And if it is like this, then you try to find the differential equation of this u, you find that it should satisfy this. So this is somehow like, then it gives you an explanation of what this differential equation, what is the meaning of this differential equation. It just somehow tells you that. But of course, the understanding of this guy, the understanding of the transport equation is again go back to what we discussed last time. It's just like for different particles, you have a movement and then they just try to move. Okay, and this is like the two ways to understand this kind of picture. And we know that from the last time, the explanation of that, we got this kind of well, transport equation. So of course, this kind of explanation or picture or geometry should also satisfy this differential equation. And you check that it is, so it must be the solution. Okay, this is actually the connection. It's connected via the physical situation or the physical phenomenon.
Okay, but then can you like how we would derive this equation not knowing the physical meaning of it?
Well, if you do not know the physical meaning of it, then you do not have any, you don't really have any real derivation of a differential equation, right? You can write whatever differential equation you want if you do not want to integrate it.
Yeah, sorry.
Right. But
I think
Mhm.
like having the partial differential equation with the transport differential equation, how do we get that derivative of a blah on t is equals to the x?
You can also
T.
understand it in this way, right? You can also understand it in this way. So again, this part is just like the derivative of this thing. Okay, the derivative in the sense of this time, the derivative in the sense of this little change of time of this kind of equation. Okay, you change this part, you change this part, but then initially it doesn't change at all. This is how this particle move. This is how the time change, but then after all, it doesn't change, right? And then if you take derivative, you find that this simply means it has, well, the partial t and partial x should have this relation. This is, if you try to see the physical meaning of partial x and partial t directly and see what's the ratio of these two meaning, what's the meaning of the ratio of these two, then I think you can only get those kind of, well, this is so-called dimensional stuff, right? You can only get, okay, the c should be of the dimension or of the label, or should have the unit as the same as the speed, okay? But it's not really, well, it doesn't really tells you, well, what is the relation of the c and the real speed of your fluid or of your dyes or of your oil or of your liquid, okay? If you try to understand it, you have to go back to this kind of control volume stuff, I think. That's a better way to understand it. Okay? Any other question? Well, okay, so this is about the transport equation. Again, as we mentioned at the very beginning, we are not only interested in transport equation because the transport equation can be seen as the easiest PDE that you can see, okay? So we also see that there are other three kind of very important PDE. That is, well, that is the wave equation, heat equation, and Laplace equation, okay? So now let's try, well, let's just change our idea about this transport equation to some other harder equation, like the second order equation, for instance, let's start with the wave equation. Okay, the wave equation is actually, well, the wave equation is actually the oldest, the first PDE that human being write down rigorously. Okay, it's not a heat equation, it's not other equations, it's a wave equation, which is somehow interesting and somehow, well, surprising in some sense. When I know this, I'm also very surprised because I thought it should be the heat equation because heat equation is more famous in some sense. But eventually it's wave equation. So how can we interpret the wave equation and how can we understand the wave equation? So what's a wave equation tells us? Well, wave equation is simply UTT minus UXX equals to 0, for instance, in 1D or 2D. Okay. So this is well, this equation tells us some story again. So this equation tells us what happens for vibrating string. Okay. So for instance, you have this frame. Okay. Whatever, it's just a frame. And on the frame, there is a string. Okay, hanging this well, between these two sticks, and this is a string. Okay, maybe you can imagine we have a string here. Okay, we have a string here, and then what you do is you try to, well, plunk it. Then it will somehow oscillate. This wave will somehow oscillate. Then the problem is, how can we describe the movement, or how can we describe this kind of string, the position of this string? Okay, this would be the problems about the wave equation. Let's say this is x-axis. Okay, this is x-axis. This is 0. This is L. And well, in order to describe how this oscillation, what is the oscillation of this string? In order to describe it, let's say at different point x, you have a different height. Okay, let's call this height u, or maybe for simplicity, let's call this the height of this point of, well, at position x to be y. Well, eventually we will say u equals to y. Okay, but at this moment, let's use y to denote it. Make life easier, because x should be represent to something alternative to y. Okay, then what we need is we need to consider the force. Okay, and see how does this y change by Newton's law. Very easy, right? Everybody knows what is Newton's law, I believe. So let's try to do an analysis of y. Let's say you try to divide from 0 to L into a lot of pieces, okay? Into, for instance, n pieces. You try to cut it into n pieces. So that is x1, x2, and 2, x capital N. Okay, and correspondingly, you have y1, y1, y2, and then to yn. Yn is well, it's a position of your this string. Okay, the height. And then let's say this is yn. This is yn minus 1. This is yn plus 1. Okay. Then we know that, and this is correspondingly, this is xn minus 1, this is xn, this is xn plus 1. Okay. Y is just a displacement. Okay. And then, well, what we do know is by Newton's law, Newton's second law, F equals to ma. Let's assume our string is homogeneous, okay? So which means you can try to imagine if you cut this string into capital N pieces, then on each this kind of vertex, or on each point, it will have the mass equals to, well, say n, well, rho times h. Okay, where h is equals to nl over capital N. Okay, so this rho is the density of this string, and then this h is how long you have for each pieces. For each pieces, what is the length of your string? Okay, then this m should equals to rho times the length. Rho times the length of your string, of this small piece of string. Okay, so that means the force should equals to rho times h times yn double prime, the accelerate, right, at this point xn. This is a force. Okay. Then you also know that, okay, this is a force, but you can also study the force on the other way, right? You can also try to do the force analysis. That is, you may have the tensor. Let's say the tensor is tau on the string. The tensor is equals to tau, right? Then what you have is, at this point, yn, it will have on this direction a tensor tau, and on this direction a tensor tau as well, right? Because the action and reaction, the action force and reaction force are the same. Okay, it's all on this spring. But then it will give you a force put down your yn, which is a force of this, right? It will give this yn an acceleration, and well, if you are able to compute this net force, then what you get is the force that gives you the acceleration at point yn. Okay. Now the problem is, what is the net force at this point? Well, the net force should equals to what? The net force should be the projection of this tau, right? The projection of this tau is well, tau times, let's say this point, this angle is theta, then it's tau times cosine theta. What is cosine theta? This would be a problem, right? So the cosine theta, well, we know that if you form the right triangle here, then you know that this shorter line of this red triangle should equals to, well, should equals to yn minus yn plus 1 from the picture, right? And then divide by this line. Well, this line, we don't really know that, but it's actually equals to, by Pythagoras theorems, it's equals to this square plus this square, right? So it's yn minus yn plus 1 square plus, okay, xn, well, xn minus xn plus 1, right? It's h squared. It's this one. So cosine theta is this. So this tau is equal, tau times cosine theta is tau times yn minus yn plus 1 divided by square root of yn minus yn plus 1 square plus h square. Okay. Now, the assumption we have is no matter how big, well, no matter how big the horizontal distance is, this yn and the yn minus 1, from the picture, you can see.
Professor, I think it's not h squared.
It's what?
Because h is nl divide n, divide big N. I think it should be just.
Oh, I'm sorry. You're right. There's no little n here. Thank you. Yeah, of course. This h is just a small value, so of course you cannot have small n here. Thank you.
Okay. My pleasure.
So, okay, that's fine. And as I said, you can imagine from the picture, yn minus yn plus 1. It's much smaller than this xn minus xn plus 1, okay? Because the oscillation of your string, compared with the total length of the string, should be small, okay? Which means, well, this yn, the distance, the length of your string, and the length of the reference x should be somehow comparable, right? So this can be seen as you ignore this part and divide by h. tau times yn minus yn plus 1 times 1 over h. You can ignore this part because h is much bigger. Okay. So this is a force from the right. Similarly, the force from the left is also time, well, this is cos theta n, this is theta n minus 1, is tau times, similarly, yn minus 1 times 1 over h. Okay? Any question? Oops, sorry. Okay. So what we get is this should equals to the summation of these two guys. Rho h y double prime in t is equals to tau times 1 over h, well, 2yn minus yn plus 1 minus yn minus 1. Okay, what's this? That is rho times yn double prime in t is equals to tau times 1 over h squared. This is yn minus, well, yn plus 1 minus yn minus 1 minus yn. And if you take h tends to 0, what you get is right-hand side tends to y double prime in x, right? Okay. So this is our wave equation. Let's use our notation u to instead of y. Then what we have is some constant times partial t u equals to some other constant times partial x u. And I think sometimes we use another notation to represent this tau over rho. That is, we use c equals to square root of tau over rho. Then what we get is, well, utt minus c squared uxx equals to 0. This c is actually the speed, the velocity of the motion. Well, from physics. I'll not explain it in math. We may have time to explain why this is velocity, but may not. Well, it depends. It depends on time. But then you can write this equation. And this is the so-called the wave equation. Okay? Any question?
I am kind of curious about its history. Can I ask here?
Yeah.
Like I remember when we were learning integral science, the equation is written as the amplitude multiple cosine something if we know this weight as amplitude.
I'm sorry, I don't really, so you can write it in like what? I don't get it.
For example, a cosine t minus something about x.
And cosine t something. I think that's for the spring, right? That's for the spring, and then you may get something like c, and that's slightly different. That's slightly different. But I don't know whether you are able to write in some other way.
Okay.
Yeah, I don't know. Well, but later you will see the solution to this 1D wave equation is also very easy. You can, if we have time today, we can see that. Okay, but it's not really looks like cosine sine. At the first glance. Okay.
Okay, but I try to calculate UTT and UXX to the wave function we had in the before, and the result is the same. It's still something like UTT minus C squared.
Yes,
UXX.
yes, that's right, that's right. But that depends on your so-called boundary condition. Okay, if you have these 2 points as the same, then basically you should have something like a cosine sign, right? Because it's always oscillate like that. But other than that, well, it depends. I can only say it depends. So which makes the general solution slightly different from what you can imagine.
Okay.
Okay, I'll show you, hopefully today. Okay. Well, maybe we should have a rest. We'll resume at 18. Okay. Now it's 8. We'll resume at 18. Okay. And when we go back, we will discuss about the heat equation. Okay, so time to get back. So that's the class. We discussed a lot about well, transport equation and wave equation. Okay, but this is just for the physical meaning of those two equations. Although we introduce the solution to the transport equation, but it's not actually. It's just because we are lucky. Okay, for the wave equation, we may not be that lucky, and we may need some other method in order to find the solution. At least in some way, in some sense, to find the solution. Okay, and then now let's consider the heat equation and the Laplace equation. They are almost the same, so I'll discuss them together. They'll always be considered the similar type of equations. By the way, the heat equation, sometimes we also call it the diffusion equation. Okay. So about this equation, it's more interesting in some sense, I would say. Maybe let me first try to tell you why this heat equation or why this diffusion equation. What does it what does it tell us? Okay, for this diffusion equation. Again, this is an equation that we can try to understand it in the sense of control volume. Okay. So this is like, again, if it is one dimension, let's again consider a water pipe. And this is x0, this is x1. You have some water flow through it. Okay. Then let's try to think about, for instance, let's say U again is the concentration of the liquid or water. And again, we have how to compute the total mass of this water. Well, the total mass of this water from x0 to x1 is x0 to x1 u xt dx. But now it's slightly different from the transport equation, right? Now it's a lot of water that's through a water pipe. Then what happens is inside of this of this piece of water pipe, the total mass may be the same, right? It may be different. It may depend on time, right? It may depend on time. So then, if we try to find the change of the mass of this water inside of this piece of water pipe, is actually equals to from x0 to x1 partial t u xt dx. Okay. Then, if we try to think on the other way, okay, what may makes the mass of water change on this piece of water pipe? This is so-called the Fick's law, which is the change of mass of water. It should equals to the water that comes in minus the water that goes out, right? Of course, this is true. I believe everybody agree with me. This must be true. How many water it gets out, how many water it gets in, and you take the subtraction, you got the change of the mass of water. Okay? But then, how can we compute how many water flows in, how many water flow out? Based on this picture, what we know is the water that comes in, right? The water that comes in depends on the speed of this water at this position, right? So it should proportional to the change of density at this point. The faster it changes, that means, well, the more water it comes. The slower, that means less water comes in. And this subtract to k ux x1 t. Okay? I think this is clear. Then that means, okay, so if we, for instance, either take derivative or divide by x1 minus x0 and take x1 tends to x0, what we get is the second derivative on the right-hand side and the, well, ut on the left-hand side, okay? So ut is actually equals to k times uxx. Okay. And well, of course, if you try to understand it in some other direction, for instance, if you try to put a, well, put a source here, you put a water spring here on your water pipe, then maybe what happens is you should add something here, right? You have add something here. Or if you try to make a hole here, then there is a sink here. Then that means you will also need to add some function here, right? This function might be negative. So which means if you add some other term in addition to this, well, to this heat equation or diffusion equation, then this term represents a source or sink. This is somehow important when you try to use this equation, use this diffusion equation, okay? And this is about the flow. This is about the diffusion, right? The flow will try to move and this kind of diffuse. Then how does that will connect to the heat problem? Well, for the heat problem, this is a little bit different. Which is
Professor.
Question?
Can I ask you a question?
Of
about
course.
the flow in and flow out part? Because taking the partial derivative with respect to x, I think that doesn't make sense. I think it makes more sense if we take partial derivative with respect to t, because it is proportional like to like the speed of the fluid go into this pipe. So I think maybe.
Remember, yes, yeah, I think I agree with you. It may not make sense, but remember, when we try to use a control volume, that means we try to shrink something in a small part of your area, right? And then control volume means you try to shrink it and eventually becomes only one point or just one piece, okay? Which is why what we are doing here is we try to either take derivative, which means either we try to find the change when we change our area, or we divide by x0 minus x1 or x1 minus x0 so that it will becomes somehow this x1 and x0 will shrink so that we can see what change in only one point, not on this whole area, on a big scale of an area. Okay, this is a point. This is so-called the control volume. Remember, this is also what we did for the transport equation.
In this case, why does the constant, the key for flow in and flow out, I don't think they are necessarily the same, because
that's a good point. That's actually a very good point. In this situation, we assume that this water pipe is a uniform water pipe. Okay, so which means this ux just means we'll assume everything just uniformly. So this ux is just will the water in just change by changing the density, because the volume are the same. Whatever you have, the volume are always the same, right? So this is why we just it has to be will only it depends on ux and k and a constant k. Okay. Where is the other page? Just a moment. I think on this one piece of my lecture notes. Okay. Where is that? I'm sorry, just a moment. Here I am. So how does it relate it to the heat problem? A heat problem. That means, for instance, we have a piece of metal and we try to understand, well, for instance, we have a piece of metal. This is really from the daily life, okay? And then, for instance, you may try to heat it. Let's say this is a candle. These are some candles. You try to heat it. Okay, you try to heat it. And then what you want to know is, after a while, what is the distribution of the temperature along this disk or along this metal disk? Okay, let's say the distribution of or the temperature at time t at position x is uxt. Okay, then we need to find what is a relation, or what is a differential equation that uxt should satisfy. Okay, and the idea is actually similar to the control volume. Let's see. Suppose again we try to make a small box here, and this box inside of the area has length h and the height h. Okay, and the middle point is x0, y0. This area is S. This whole area is S. It's a small box. Okay, we try to study the heat problem on this small box. Then the thing is, okay, you have this small box. What happens is, well, let's consider the total energy. The total heat energy. Of course, the heat energy, it's it can be written as, it depends on the temperature of this area, right? So this heat energy, let's say, is ht, then ht should equals to, well, proportional to the integral along S, the whole area, well, this whole box of this u x comma y, we are in this two-dimensional plane, u x y t dx dy. Okay, it's proportional to the temperature. The heat energy only depends on the temperature. That clear? So sigma is greater than 0, depends on the material.
Why is it linear?
Wait a moment. Because this is a definition of heat energy, right? What is a heat energy? Heat energy is only depends on, it's a constant times times your temperature, something like that, times the area. This is a definition of heat energy. So we have this. Then again, let's try to consider the change of your heat energy. of your this piece of disk or this S, a small box. So it's equals to, well, on one side, ut. Or if we want, if you do not like this kind of double integral, then we can also write it as sigma h squared, well, sigma times this h squared times partial u partial t at x0, y0, t. Okay. Okay. Now, again, we need to find what is, well, what will depend, how does this kind of energy change? Will depends on this so-called heat flux, okay? The flux of your energy. By the way, this is not really something about physics because I'm not a physicist. What I'm talking about maybe in the future after you learn some serious physics class, maybe you are laughing at me. But whatever, this is, well, basically what mathematician will think about this kind of problem, okay? The heat flux. Then we can use so-called the Newton's law of cooling, or somebody call it the Fourier law. The Fourier's law. Well, by the way, Fourier is famous for his study in this heat equation. And the heat flow. The heat flow from the higher to lower temperature at reach proportional to the difference of the temperature. The difference or the gradient. The gradient of the temperature. Which means if you have something very hot, very heat, and something very cool, then on the transition part, the transition will be very quick. The heat flux will be very big. Okay. Otherwise, if the temperature of them are very similar, then they may not transit their energy. The heat energy may not change a lot, or at least not so fast. Okay. So based on this law, what we have is, well, let me draw this picture here again. You have this as S, this point is x0, y0, and then let's say this point is x0 plus h over 2 and y0. Okay, so you want this heat flux. You want, just like the flow, some heat will go outside of this box or inside of this box, depends on the side. Okay, then we know that from this side, the flow you will lose the heat energy, or the heat energy will change something perpendicular to, or not perpendicular, proportional to the length of this line times partial u partial x, which is a derivative of u on this line. Okay, evaluate at x0 plus h over 2, y0 at t. Okay, with minus sign because in our notation it will just go out. Okay, similarly it will go this direction, it will go this direction, and so on. Okay, so this means partial h partial t is approximately some constant times h times partial u partial x, evaluate at x0 plus h over 2 y0 t, minus partial u partial x x0 minus h over 2 y0 t. Okay, plus partial u partial y x0 y0 plus h over 2t minus partial u partial y x0 y0 minus h over 2t. Okay. So maybe the picture I draw is not so clear here, but you should try to imagine it's somehow like the heat energy will try to change, and it will proportional to this kind of derivative. Okay, on the border, on the boundary. So if you take h tends to 0, what you get is again, h tends to 0. So you have to divide h squared both sides, and then what left would be this term, and what you will get is sigma over k partial u partial t is equals to this plus this. Okay. By the way, so personally, this kind of thing, this part of this proof, you cannot find it on our textbook, on the Water-Strauss textbook, but you can find it on the Stan's textbook. Okay, you can find on Stan's book on the first chapter. If you're interested, you can try to read it by yourself again. Okay, but personally, I don't really like this kind of thing because it's really confusing, and it makes everything without the integration and makes everything kind of discrete. So if you are familiar, which I hope you are, if you are familiar with those kind of divergence theorems or this kind of formulas, then what I would recommend you is you can also try to conclude this kind of thing this way. The derivative of your energy, of your heat energy, is equals to the double integral partial u partial t dx dy. And the Newton's law of cooling tells you it's actually equals to on the boundary. On the boundary, you take the boundary integral, and you know that it will go outside, so which means it's actually n. N is the normal vector of the boundary of S. Okay, so which means on this line it's go out, on this line it also goes out, and go out and go out. And then times the gradient of u. N times the gradient of u, d partial S. Okay, partial S means the boundary of S. This is just notation. Okay, or you can use some other notation. This is actually partial m, partial u, partial n. Okay, you take the derivative in the direction that perpendicular to the boundary. Then by the divergence theorems, this line integral, you can try to do an integration by parts. Okay, you can do an integration by part, somehow like an integration by part, and make it somehow the plane integral, the double integral. So it's equals to kappa divergence of n there's no n, divergence of gradient of u ds or dx dy. Okay, and then the divergence of gradient is equals to Laplacian. You can check yourself. The divergence of gradient is equals to Laplacian. Okay, so it's equals to kappa s Laplacian u. Well, k the s Laplacian u. Okay, so this actually also gives us another kind of generalization of the heat equation, which is if your K, which is, well, the parameter of conduction, right? If your K depends on space, or even depends on time, but we usually not say it depends on time. That's very unusual. Then from what we get here, we will have, well, this, well, partial u, partial t, dx, dy should equals to kn times gradient of u d partial s at partial s. By divergence theorems, what you will get should be, you take this, well, you take another derivative here, divergence here, I mean, kappa gradient of u. So generalized form of a heat equation should be written as this. And well, sometimes if you study this elliptic equation, you call this type of equation still a divergence type equation, okay? But this is just something that you might need if you are doing something more applied, okay? If you are doing something in engineer. So before we move on, any question about this heat equation? This is just some different forms of the heat equation. And of course, well, this course, I will just let you know this intuition. And I will not let you know, well, I will not ask you to really solve this kind of thing by yourself, okay? But I hope you, I hope you have the idea of this kind of intuition, okay? This is very important, and it's especially important when in the future you're trying to study this kind of mathematical modeling or something like that, okay? Study some engineering problem or physics problem, okay? Any question?
Oh, actually, is our homework uploaded yet? Cause
Not yet, not yet. I will upload it very soon. Yeah, when I upload our lecture notes, I will upload the homework. Okay.
okay,
So
thank you.
maybe like 7, around 7. Okay. Your homework will be on will be the problems of chapter 1 of Strasbourg. Okay, Water Strasbourg will be well. I think it's the first week's homework is not so hard. I think it's not so hard.
Sorry, I have one question.
Of course.
On the last page, like no, like the page on the right. Yeah.
This one.
The longest equation in the middle.
This one. Mm-hmm.
So can you explain the sign of each?
Yeah, that's a very good point. Why this sign to be this? This is plus, this is minus, this is plus, this is minus, right?
Yeah.
Not so clear from this picture. Yeah, I agree. It's not so clear from this picture. And you can just imagine it's like, this is why I would suggest you try to understand it this way. Okay, so if you try to understand it this way, then it's easier for you to understand because it's just everything just to normal vector times the gradient of u. Okay, the normal vector is just everything go out. Okay, you can try to read Stan and see whether you understand it or not, but this is it's a little bit tedious. So yeah, I'll leave it as an exercise. Try to think it yourself. Okay, it's on Stan's book, first chapter and heat equation.
I think the sign is just because that we should treat the curve. How do I say the curve? I mean the edge of this area like counterclockwise. So this is plus, this is minus, this is plus, this is minus.
Yes, sort of like that. But this is kind of physics, and since we didn't discuss rigorously about this Newton's cooling law, so it's kind of hard to try to explain why is alternative. okay? Because, well, I'm not physicist, I'm not doing a physics class, so, well, read it yourself, okay? And I prefer to understand it this way, if you are good at this divergence series and these vectors.
Yeah, I will check it. Thank you.
Okay. Any other question? Okay, now let's move on and let's think about, well, right now, at least we have the object we try to study in this semester, okay? We have the problems, we have the 4 very basic differential equations, and it looks very easy for most of them, and it seems that, oh, sorry, I forgot. I forgot the last thing, that is a Laplace equation, right? Laplace equation seems to be where you do not have the right-hand side, right, of the heat equation. So what's the meaning of a Laplace equation? Well, as long as you know what is the meaning of the heat equation, you absolutely understand what is the meaning of this Laplace equation. What is Laplace equation? It's very simple. You have the heat equation. What if we wait for a long enough time for the heat equation?
The temperature reaches an equilibrium.
Yes, exactly. So if we wait for a long enough time, then the temperature shouldn't depend on your time, right? After a while, it should become somehow stable. Although it's not a constant temperature, it may not be a constant temperature, but it will be something, well, does not depend on T. After a while. So this is like a steady state of the temperature. The steady state of the temperature is, well, it's a temperature that satisfies the Laplace equation. This is, I think, the best way to understand the Laplace equation. Okay? Very easy. Moreover, for Laplace equation, or in the future, maybe I'll tell you, the elliptic equation is, it can be seen as a steady state of the heat equation. However, for people who study this elliptic equation and the so-called parabolic equation, they find that they share very, very similar properties. Okay, so which means as long as you know the steady state of this temperature, you can get a lot of information about the temperature evolution of your temperature. Okay, so this is something very interesting, which well, if you're interested, you can try to learn something. Okay, what is a connection between the heat equation and Laplace equation? Okay, so now we have the basic object of the things we are trying to learn in this semester. Okay, now we have to make the object very rigorous at this moment. Okay, we now have several equations we want to study, but then what is the property that we want to study of these equations? If you want to study the solution, then it seems that, okay, at least for the transport equation, we know everything, right? We can even write down the solution. Is that enough? Not really. Okay, not really enough. So we have to make our problem rigorously and see whether we study this problem, well, good enough or not. Okay, so first, let me make the problem rigorous so that it forms a problem. Okay, let's discuss about the initial value and boundary value. The initial conditions and the boundary conditions. It is some initial state or the initial status of your physical situation, of your physical experiment, okay? Which is something so that, which is some starting point so that you can try to start to solve a PDE. You can see that for the transport equation, For the transport equation, ut plus c ux equals to 0. You find the general solution to be some function, and well, I think it's x minus ct. It will be solved in this way. But then you find that it is a general solution, but what is f? This is something where you have to determine, you have to tell me, right? So which means if you really want to solve this differential equation, you may need some more condition instead of only this differential equation. It's not like an algebraic equation so that I write down the algebraic equation, you can solve it, right? And it's not really like the ordinary differential equation, because for ordinary differential equation, as long as you know the initial time, you know the initial data, you always, well, you almost always be able to solve it or tell it is the solution does not exist, okay? But for partial differential equation, it's slightly different. It can
Professor, I can't hear you. Professor, I can't.
I hear you. I hear you. I also see that. It seems that my connection is not stable. Is that okay now? A little bit?
Yeah,
A little better?
now.
Sure.
Okay. Well, I don't know how. I don't know why, but yeah. Hopefully it will be better. Okay. So we have a differential equation, especially for instance, the heat equation. Okay. If you do not have any derivative in x here, then this equation is quite easy to solve, and you only need one initial condition, right? You only need to tell me what is ut at 0, right? But now what happens is this change in time, it actually depends on the accelerate or the second derivative of u in x. Okay, so this is a different story then. Then that means if you try to find the function of u, maybe the initial value can tell you what happens of this u depends on t, because you know u at 0. Then if you know the derivative of u, you will know what is u at 1, you will know what is u at 2, because you know the change of rate, so you know everything, okay? But for a partial differential equation, this is for ODE, but for a partial differential equation, you know u at 0. This may not be enough, because the connection between u at 0 and u at 1 is on the second derivative in x, right? So this may not be very clear to see how you can connect the initial and then the change of rate, and then you get u1, okay? So which is why the initial data may not be enough for partial differential equation. So what do we need? What do we need? Well, for instance, I hope you have seen this kind of problems in ODE, okay? Suppose we do not have this partial xx here. We only have this partial tt here, and you have partial tt u equals to u, okay? Then how many initial conditions do you need in order to determine u?
1.
Is 1 enough?
Oh, sorry, 2. Because it's of second order.
Yeah, it's second order, so which means you need 2. Why is that? It's simply because if you know only u0, then what you know is from the right-hand side, you know what is the second derivative of u, right? So in order to get u1, you will need u prime at this moment, right? So which means one condition may not be enough. You may need another condition like u prime at 0, so that you will know u prime at 0. From u prime at 0, you will know what is u double prime, and you will know what is u prime at 1, and so on, right? So you know the accelerate. That means you will need your initial position, you will need your initial velocity to determine the displacement at all the time. Okay, so similarly, if you see that like a wave equation, then, well, usually you will need two initial conditions in order to determine the solution, if we only discuss about the time, okay? There is no rigorous proof about this kind of criteria, but well, this can be seen as a general criteria or general voodoo. You can imagine that is always true. Okay. This is for if you try to look at the PDE only on the derivative in time. Then the things will be very easy, because if you try to think about the time, then probably, okay, the time can only be, it cannot be, you study this differential equation in a very weird time area, right? The time only have one dimension. But if you try to study the space, if you try to study this x, y or xy on some domain, and you try to study the evolution of your solution, then the problem becomes harder, right? You can try to imagine the x, y are in this S. Then the problem becomes try to solve some physical phenomenon or physical experiment along this area, right? And in this case, you may need some kind of a boundary condition in order to study this problem. This is a boundary problem. Well, let me use abbreviation, the boundary condition of PDE, okay? For the derivative in time, it's quite easy to deal with in the sense of initial data, but for the derivative in space, it's a little bit hard. Here, in physics or in this kind of applied math, the boundary condition always consists of 3 types, okay? The first type is so-called the Dirichlet boundary condition. Okay, this is so-called the Dirichlet boundary condition, which is, for instance, if you have this kind of area, let's say this is not S, this is D, make it easy, uniform notation. And I will let you know what is the value of U on the boundary of this domain, okay? Or if it is in 1D problem, like the wave equation, I may tell you the boundary of your wave, right? The boundary of your string. For instance, what is the boundary of the string? If this is 0, this is L, then that means I tell you the boundary condition. That simply means I tell you what is U0t and is equals to ft, what is ULT. which is gt. Okay. So for instance, in a wave equation, I probably need to tell you what is u at 0, the distribution of this u, of this position displacement of u at 0, and what is the derivative in time of this u at 0. And I also need to tell you what is the boundary condition of this string, so that you might be able to solve the equation. Okay, so more or less, you can imagine why is that. It's simply because, for instance, well, like the heat equation, you know the, well, you may know, for instance, the heat equation. You have a rod or a stick, and if I want to check what is the temperature on this stick, okay, then you should tell me what is initially the distribution of temperature on this rod, okay, and then you should tell me, okay, whether you have put 2 candles on this side and this side of this rod so that it heated all the time, or what is the boundary condition? What is on the boundary? Your temperature. Okay, this is for the heat equation. Then you can imagine in this situation, in this kind of physical situation, the temperature at each moment of the stick should be determined. You can imagine, right? Or if it is in 2D, you're in a disk, then, well, I should tell you, okay, first, what is the temperature of your stick, of your disk, and second, whether you make it heated around the boundary or not, right? If you make it heated, like the temperature on the border is always 100 degrees, then okay, I know that. Then I know that, okay, the temperature inside should be computable. It cannot be something. It cannot be something else. It can be a unique situation, right? This is why this kind of situations are always necessary and always sufficient in order to determine whether the solution exists or not. Because this experiment or this kind of situation is unique. You can imagine physically. No proof, but you can just imagine. Okay? So sometimes we just write it as U restrict to partial D equals to F. Okay? F is a function on the boundary of your domain. This is so-called the Dirichlet boundary condition, which is just tell you the value of your function on the boundary. And another type of the boundary condition is so-called the Neumann boundary condition. The Neumann type boundary condition. That is, I don't really tell you what is the value on the boundary of your disk or whatever, okay? But what I can tell you is the normal derivative, or this n dot gradient of u on the boundary. For instance, is equals to g. This is a very typical Neumann boundary condition for a partial differential equation. What's the meaning of that? What's the physical meaning of that? Well, again, if we're trying to consider this diffusion problems, the heat problems, this simply tells you what is the speed of the flows in and flows out on the boundary, right? What's the meaning of this? This simply means what is the change of rate on the boundary which perpendicular to the boundary, okay? So as long as I tell you the rate of change along the boundary, and as long as I tell you what is the initial status of this inside of your domain, then the situation or this physical situation should be determined. Question?
Does En represent the normal vector here? Because
Yeah, n is a normal vector of the boundary of D. Okay, so this represent the flow in this diffusion problem and flow out, or it's just the change of flow. Okay, and well, what if you have this so-called the homogeneous Neumann boundary condition? This makes a lot of sense, I think. This simply says that the homogeneous Neumann boundary condition simply means your flow will not get in or get out, right? It will not linking, or it will not try to compress, because orthogonal to the boundary, there is nothing, okay? There is nothing go out, nothing go in. Or on the heat equation, this zero Neumann boundary condition simply means you have a perfect insulate. It will not transit the heat energy with outside. Okay, it just fix it. But be careful here. Neumann boundary condition and Dirichlet boundary condition are not the same. Okay, you see, even you have a zero Neumann boundary condition, the flow on the boundary or the density on the boundary may not be zero. Okay, well, for instance, you have the perfect insulate, the perfect insulate, then the boundary may have some temperature. It may not be zero temperature, right? It just does not talk to the outside. The temperature here could be 100 degrees, but outside it could be 0 degree, right? But then, as long as you have a wall here, it can help you to avoid the inside and outside to talk. Then this also satisfies this zero Neumann boundary condition, but it's not zero Dirichlet boundary condition. It doesn't say anything about what is the value on the boundary. It just says that it doesn't talk. Okay, it does not talk outside. Okay, any question? This is a physical understanding. Of course, as a math problem, you don't really see that physics, okay? But I still want you to try to understand it in terms of physics. Okay. And there is another type of, so-called a mixed boundary condition. It's so-called the Robin boundary condition. This is, you have mixed, which is you have both the normal direction and u, okay, is equals to something. This kind of boundary condition is so-called the Robin boundary condition. Well, it's in physically, Robin boundary condition, or in engineer, Robin boundary condition is very useful. But here I will just give you one example, because mathematically we don't really use this kind of Robin boundary. Well, we use Robin boundary condition, but we can somehow make it simpler in some sense. Okay, for instance, you have a rod. And again, we study the heat. We have studied the heat equation or the temperature on the rod. This is a boundary. And then what happens is there is something. There is like a piece of coral, okay, or whatever, so that it is always the temperature is always equals to G of T, and you put it on the end of this rod. then what happens is, well, it satisfies the Fick's law or the, well, Newton's law of cooling, okay? Such that the change of this, well, the gradient of the temperature at the boundary should be proportional to the temperature change or the temperature difference, okay? U0T minus GT, which is a very typical Robin boundary condition, okay? But again, let me repeat this. All this kind of boundary condition, mathematically, this just means some kind of, well, functions. I gave you some values and so on, okay? But physically, it doesn't make sense. It does make sense, okay? However, this is a math course, so I will just tell you this background, and in the future, some kind of background may help you to solve some problems, but they will not be essential. This will be crucial when you really want to use them in practice. That's something crucial, which is why I introduced this kind of thing to you. And of course, I will not test this kind of thing to you. Okay, I will not test you this kind of thing, and well, which is a Robin boundary condition, which one is Robin boundary condition, what's the meaning of Robin boundary condition in this problem. This is a math course, okay? This is not really a language course. This is not really a literature course. So I'll not ask you to write some article about it. And I personally, I don't really want to write this kind of article about, well, the explanation of this kind of equation. But, well, this kind of explanation or this kind of intuition may be helpful. For the problem I ask you to do is just a math problem. But sometimes it may help you to understand this math problem in the sense of physics, okay? Not necessary, again, not necessary. Any question? There are several other types of very weird boundary conditions that we might use in this semester as well, okay? Maybe I'll just mention this. Something not very typical, but also somehow useful when you try to study some particular area. This is really something that's made by mathematicians, not really physicists. The condition at infinity. Okay, for instance, if you try to study a problem of half plane, okay, then if you try to study, for instance, the heat problems on the half plane or the flow problems on the half plane, then maybe the boundary condition is just on, well, what happens on this part, right? This could be a good boundary condition. However, if you try to imagine, then it looks like not very good sometimes when you try to think it mathematically. So if you have an unbounded domain, then sometimes you may need some other condition of your solution at infinity. Well, maybe not only the half plane, but unbounded domain. Then you may need some condition of your solution at infinity. Okay? So for instance, you may need to ask your solution to disappear at infinity, and so on, okay? You will see one example in your homework, this type of examples. Well, mathematically, that simply means you try to study this domain and you try to complete the topology of the plane so that at infinity there is one point. And this can be also be seen as a boundary of your domain, okay? And another type of, well, very interesting example is sometimes, especially for me, my research are studying something untorus, like a donut, okay? This is a torus. What is a torus? Or T2, okay? Two-dimensional torus. What is a torus? A torus is something consists two variables, and both variables are periodic. Okay, it can be seen as you have two variables, and both variables x and y are in S1. So which means it has a period 2 pi. Okay, so you can see that a torus, if you study problems on a torus, then you cannot find any boundary of this torus, right? This geometric object does not have a boundary. So in this sense, if we study some problems on a torus, we may say that, okay, we study the periodic boundary condition. In the sense that, although there is no particular boundary condition, but we want our solution to be periodic in terms of two variables. That means, well, for instance, T2, ut0y is equals to ut1y with period 1, and utx1, well, 0 is equals to utx1. Okay, this could also be a boundary condition. Topologically, this is just something like infinite, well, I think I shouldn't say this kind of thing in topology, but as long as you know what is topology, maybe you get a better idea about what is a torus, why we are interested in torus, okay? And in Fourier analysis, this is especially interesting. It will be an interesting problem, okay? To study a differential equation on torus. And another very, very real case about this boundary condition is so-called jump condition. For instance, you may have a piece of materials and it's made by two kinds of things. Okay, this part is made by iron, this part is made by copper, and then you study this heat problems on it. This is very important in the engineer, but this is not very interesting in mathematics. Okay. So if you have this kind of materials, then the hard part would be how you can define well, a boundary condition in the middle, okay? So that you will have a solution and it makes sense physically, okay? D, for instance, equals to D1 unit D2. And then you may have a boundary here as well. This will be harder problems when you try to face, okay? So those are all kind of boundary condition, physical boundary condition we may be able to see in this session, okay? And I think you will be able to see in the future if you have some problems in terms of PDE or and engineer or physics. Any question? Any question? Any question?
Well, I have just too much.
Okay. Well, you should try to make well, each questions very clear, and then you can ask me. Okay. So the last thing I would like to mention a little bit is well, it's so-called the well-posedness of the PDE. You can see that at this moment we do have everything about studying a PDE problem, right? we do have the object that is 4 types of, basic PDE that we try to study. And as long as we give it our initial condition and boundary conditions to those 4 types of PDEs, then we are able to study it. But then the next question is, what kind of problem, what kind of properties we are asking for those PDEs? This is so-called the well-posedness problems of a PDE. Well, sometimes I think if my memory is correct, this is so-called the Adama's 3 principle. Adama, am I spell it correctly? Adama? Well, I think it's somehow spell it like that. I think you know who is Adama. He's a very famous mathematician. And to study a PDE, or to study a PDE with initial condition and boundary condition, to study a PDE, well, we are basically studying 3 things, okay? First thing is, we try to study whether, based on this initial and boundary conditions, you have a solution or not. This is so-called the existence. Well, whether you have a solution or not, this is always the first thing you try to ask yourself when you have a math problem, okay? Which seems to be trivial, but it is actually the hardest part of problems, especially for PDE problems. And second thing is whether the solution is unique or not. So which means there is at most 1 solution. Okay. And the reason why these 2 are so important to a PDE is quite obvious, right? If you have a differential equation, then of course you try to find a solution. Then the existence and uniqueness are the first thing you try to ask yourself. Of course, if you are able to write it down, then the existence is no problem. If you cannot find any other solution, then the uniqueness is not a problem. But on the other way, if we try to think about a PDE is just telling you a physical story, then you can see that what are these 2 asking us to do? The existence just says that, okay, based on the known things, based on this kind of theory, like Newton's 2nd law, and the initial state and the boundary condition, whether your physical phenomenon is uniquely happen or not, right? This is a existence and uniqueness. If you do want to have some PDE that makes sense, then yes, of course, you do want it to have an existence and a uniqueness of the solution. Otherwise, either this physical situation could not happen, or you cannot determine a unique physical situation or physical phenomenon, right? For either of them, it is not satisfied for your physical study of something, right? So which is why existence and uniqueness is not only interesting for mathematics, for mathematician, it's also very, very important for physicists, okay? And the third part is so-called the stability. Well, this part, I think if you learn this ODE course, you may have some idea about what's the meaning of the stability. The stability is, whether the unique solution, you can see that this is the most basic one, this is the second stage, this is the strongest stage, okay? If you have the existence of the solution and the uniqueness of the solution, then you are able to study whether it's stable or not. This solution is stable or not. Whether the unique solution, UXT, depends in a stable manner on the data of the problem. Physically, what's the meaning of this? Well, physically, it just means that if you're doing an experiment, a physical experiment, and you have all these kind of initial conditions and whatever, okay? You have all this kind of source, and you have this kind of initial condition, you have the boundary condition, everything you set up. But when you try to do an experiment, well, you are not able to handle everything. There will always be some machinery error of your experiment, right? So the stability will guarantee that even if you have some error on your initial data or some input data, your output is still something makes sense. You have very small perturbation of your initial data, then eventually your output should also be somehow very small perturbation of the correct experiment. Okay? Otherwise, this may not be a very good experiment. Otherwise, this may not be a very good solution. Okay? Which is why you may want the PDE, a PDE with initial and boundary condition, have these three properties of its solution. Okay? But it always be very hard to study these three kind of things. Maybe I will just give you one examples about about stability. Okay, for instance, the so-called the backward heat equation or the backward diffusion equation, which means of course you have the heat equation, you have the diffusion equation, then you may have something very good, right? If you have some sense of the chemistry or some other sense, you may know that if you have some diffusion process, then it will basically make everything super smooth. If you have some heat problem, then eventually the distribution of the temperature should be somehow very, very smooth on your domain. Okay? So what happens? So which means the solution starting from something very rough initially, eventually will becomes very smooth, and some norms or some kind of quantity should become smaller and smaller. Because the energy, if you try to see that, if you try to see the diffusion process, the energy will disappear, somehow be smaller and smaller. Okay? But if you go back in time, this also means that if you starting from something very smooth, something very small, and you go back in time, then what happens is, you may get something very rough, something very big. Okay? So which means the backward heat equation at least should be unstable. It will not have some stability of the solution. Okay? And maybe I'll give you another example just to give you some better understanding of this existence, uniqueness, and stability. Another example is when you try to, for instance, not solving a PDE, but solving a linear algebra problems. Okay? U equals to B, U times A equals to B. Then you know that if you wanted to have a solution, then you must have something like the dimension of U and dimension of B should satisfy some condition. If you wanted to have a unique solution, then you may even need a better restriction on the dimension. Okay? Even more, if you wanted to have a stability of your proposition, a stability proposition of your solution. Here, the stability proposition maybe should in the sense of numerical computation. Then what you may need is this matrix may need to have some, for instance, the eigenvalue of this matrix shouldn't be over too small, right? For instance, if you have 0.0001 times x equals to 5, then, okay, you know that this x should equal to 50000. Okay, this is something you can compute by your hand. However, if you try to compute it by your computer, by MATLAB, for instance, then, well, if you have very small number here, then this x, if you use a computer or a calculator, it may not get some result like this. It may be somehow very chaotic. Okay, so which means if you really want this problem to be stable in the sense of numerical analysis, then you may need some other restriction on it. Okay, I think I should stop here, and sorry for late, and I think I late for, well, I somehow delayed for 3 minutes, so sorry about that. And that's all for today. I will see you next week. Okay, again, I have my office hour from now to 6. Okay, if you have any questions, you can let me know. Otherwise, feel free to go.
Oh, I have 2 questions.
Of course.
One is about let me see.
Which one?
Is in this equation.
Which part?
Fick's law.
Fick's law. Okay.
Yeah.
Fick's law, I think is somewhere the Robin boundary condition, you mean?
No.
Or
It is before. Like when we first go to the heat equation.
the heat equation part. Somewhere here, right? Should be somewhere here. The diffusion equation should be somewhere here. Right? Here.
Oh, yes.
Mm-hmm.
I'm kind of confused how we get to ut equals to kuxx, something like that. Yeah.
Well, you can see that here it is x0, x1, well, from x0 to x1, right?
Yes.
Divide x1 minus x0, and also divide it here, and take x1 tends to x0. Then on the right-hand side, what you get is, well, this inner part, fundamental theorem. Or this is something, I forgot what's the name of that. But it's, it can be gotten from the fundamental theorem calculus, right? On the right-hand side is uxx.
Yes.
Mm-hmm.
I'm okay with here, but then how we get ut?
Well,
how we get the equation below?
Oh, ut here. You see here is ut.
Yes.
Right? This one goes to from x0 to x1, partial t u dx, right?
Yes.
So if you divide x0 minus x1.
I understand it. Yeah.
Mm-hmm.
Another question is about the wave equation.
Okay,
like,
the
I
wave
am
equation.
thinking, the wave equation here, like how we analyze it, doesn't mean the wave is like, so you don't need to assume the wave is a harmonic wave. Like the wave function here can describe any wave.
Yes, it can be any wave, exactly. So it may not be somehow periodic, for instance.
Okay.
It could be anything in this. Well, today we don't have time to really solve this wave equation, so that you don't have a good idea about, well, what's the solution of this wave equation looks like. And actually, the solution to this wave equation is actually a long story. But I think we will do that on Tuesday. Okay. And you will see, okay, there is an easier way, a very easy way to see the solution of this wave equation. Okay. Mm-hmm. But at this moment, for those kind of problems, other than the transport equation, don't try to imagine what the solution looks like. Okay. Or try to imagine, but well, later we will have some other way to solve it.
Okay.
Mm-hmm.
I just remember, like, before if we look at the harmonic wave, if we know the speed of the wave and the amplitude, and we can get a wave function of what the wave is like at a certain point.
Mm-hmm.
Like I was curious what the relationship between this equation and the wave function we have here? Like, do they have a story, historical story behind?
Yes, there is actually a historical story behind, but not really actually. It's a very it's so-called the D'Alembert solution to the wave equation, and it's quite simple. You can check it, and about why it looks like this. Why it looks like somehow like a harmonic function, right? Why it looks like sine cosine function is simply because if you want to find some functions looks like this, right? Starting from something and you have some kind of it has some plastic and it somehow satisfies the Hooke's law, right? If it has some, well, it is somehow like a elastic string or something like that, then maybe locally it will always be like a cosine sign. Okay. However, in general, if you do not assume this kind of Hooke's law, if you do not assume this this string is like an elastic string or something like that, then maybe you get something different. Okay. Mathematically, you will see that you cannot really see anything. Yeah, you can try to Google what is the D'Alembert solution. And
how to spell the D'Alembert?
D'Alembert. Let me see. Spell it correctly. D'Alembert. And you can also check this from the Stan's book. Okay, on Stan's book 1, it also have this solution.
Okay, I'll check it.
Mm-hmm.
Thank you.
Yeah.
I don't have any other questions.
Okay.
Bye.
So if you have any other question, now I already make it active for this so-called, what is the name of that? The breakout room. So if, where is that? Where is the breakout room? Oh yeah, let me, so I